In the late 1960s, an 8,500 horsepower locomotive tears across Wyoming's high desert, trailing a 30-foot exhaust plume hot enough to scorch trackside vegetation. Union Pacific called it the Big Blow. By 1977, everyone was scrapped. It wasn't alone. An entire generation of mad genius locomotives pushed technology past the breaking point. The question isn't just why they failed, but why anyone believed they would work. A locomotive nearly 180 feet long, the Union Pacific GTEL, nicknamed the Big Blow, cuts a striking figure across the Wyoming desert. 3 hulking units move as one: a control cab, a turbine powerhouse, and a fuel tender as large as a tank car. At full throttle, the Big Blow unleashes 8,500 horsepower, a number that once set the standard for rail power. For context, a Boeing 747-100 fuselage is only about 50 feet longer, and the comparison feels almost trivial when the two are side by side. The Big Blow's presence is unmistakable. A 30-foot exhaust plume trails behind, shimmering with heat and leaving a haze that hangs over the tracks. The roar is relentless, and crew members remember the sensation of being inside a jet, the cab rattling as the turbine spins up to 20,000 RPM. The startup is a ritual, a low hum, then a piercing shriek, and the sharp scent of hot metal and diesel filling the air. Exhaust temperatures hit 1,200 degrees Fahrenheit, enough to scorch grass and blacken wooden ties along the right-of-way. Maintenance logs from Cheyenne record burns within 30 feet of the line, and complaints about scorched earth stack up at the Interstate Commerce Commission. But this machine is built for scale. The GTEL hauls mile-long trains, sometimes 12,000 tons of freight, across the high desert at 60 miles per hour. The promise is more power, fewer locomotives, and the ability to move massive loads with just one crew. Test reports claim 0.36 gallons of fuel per ton mile, a 37% edge over the best diesels of the era. Yet every mile brings a cost. Turbine blades, crafted from nickel alloys borrowed from jet engines, erode under the constant assault of sulfur-rich fuel. Mechanics inspect for pitting and cracks every 4,500 miles, replacing blades before disaster strikes. The 24,000-gallon tender barely covers a single run across the overland route. Inside the cab, the crew faces 106 decibels of noise, relentless vibration, and heat. The Big Blow's power is undeniable, but so is its appetite for fuel, for parts, for human endurance. Even as it outpaces rivals, the first cracks are visible: scorched earth, worn blades, and a maintenance burden that grows heavier with every run. During the Second World War, steel and copper were rationed by government order. Railroads found themselves at the back of the line, their diesel orders delayed or canceled outright as the War Production Board funneled high-strength alloys to aircraft factories and shipyards. In this climate, Union Pacific's management weighed every procurement against a backdrop of scarcity. Chief Mechanical Engineer Robert H. Miller and his staff combed through memos from the Office of Defense Transportation, searching for any loophole that would keep freight moving across the continent. The GTL concept gained traction not just for its horsepower, but because it could be built using surplus turbine-grade alloys, materials suddenly available after the war's end, when military contracts dried up and government warehouses overflowed with unsold jet engine parts. By 1948, Union Pacific's boardroom saw opportunity in adversity. Internal correspondence reveals executives captivated by the idea of transferring aerospace breakthroughs directly to the rails. General Electric's sales pitch leaned hard on this vision, promising a locomotive powered by the same turbines that had propelled fighter planes over Europe. The GTEL's turbine core was adapted from the J-47, a mainstay of early jet bombers, and General Electric's marketing literature boasted of a machine that could thrive on low-grade bunker C oil, fuel so dirty and cheap that it was considered a waste product by refineries. This was more than technological optimism, it was institutional strategy. Wartime scarcity had taught railroad leadership to favor bold leaps over incremental gains. The GTEL's projected fuel economy, measured in gallons per ton mile, looked compelling on paper, and with the promise of moving mile-long trains with a single crew, Union Pacific's cost-benefit models showed millions saved in labor and motive power. Board minutes from 1952 capture a mood of almost feverish confidence. If America could build the B-29 and the atomic bomb, surely it could conquer the mountains with a locomotive that ran on jet fire. The post-war years were flush with this kind of thinking. Government procurement archives show a pattern. Surplus materials released to civilian industry, a glut of aerospace-grade metals, and a rush by manufacturers like General Electric to retool jet technology for the peacetime market. Managerial incentives aligned around scale, novelty, and the allure of outpacing rivals. In this environment, the risks of blade erosion, thermal stress, or noise seemed manageable, mere engineering puzzles to be solved on the fly. The GTEL was not an outlier, but the product of a system primed to gamble on the next big leap, convinced that the future would reward those who moved fastest and thought biggest. On the Southern Railway in 1942, Oliver Vaughan Bullard faced a different kind of scarcity. Wartime steel and copper rationing forced every design decision to be filtered through the lens of material thrift. The result was the Q1, a locomotive stripped to its core. No side windows, no decorative brass, not even a full-length smoke deflector. At just 55 tons dry weight, the Q1 was the lightest freight engine of its class in Britain, yet delivered a tractive effort of 26,500 pounds force, enough to move heavy coal and munitions trains across the southeast. The Q1's bare steel and blocky silhouette became a symbol of wartime austerity. Bullard's design drawings, preserved in the National Railway Museum, reveal every ounce shaved, every non-essential part omitted to meet government quotas, but the savings came at a cost. Crew diaries from the Southern Railway Archive describe the cab as cramped and bitterly cold, especially during winter runs. The lack of side glazing left drivers exposed to rain and coal dust, and the simple controls, while easy to repair, offered little comfort on long hauls. Maintenance crews appreciated the reduced number of moving parts, but footplate staff often complained of fatigue and poor visibility. The Q1's service life stretched from 1942 to 1964, a testament to its ruggedness, but also a reminder that engineering for survival can clash with the day-to-day realities faced by those who operate the machine. Propeller-driven railcars promised to bring aviation speed to the rails, but the physics of flight clashed with the realities of the track. In the late 1930s, German engineers tested the FSL-1, a streamlined car with an aircraft propeller mounted at the rear. On a straightaway, it reached 150 kilometers per hour, a headline-grabbing result. Yet as soon as the railcar entered a curve or met a strong crosswind, trouble started. Tests recorded yaw instability beyond safe limits, with the car swinging several degrees off-axis at speed. Accident files from the Ministry of Transport detail 3 derailments directly linked to this effect. The exposed spinning blades posed a constant threat to anyone on the right-of-way, and the propeller's roar made conversation inside nearly impossible. Efficiency figures from Fairbanks Morse's U.S. trials showed only 12% propulsive efficiency at 80 kilometers per hour, well below that of diesel electrics. High-pressure steam prototypes ran into different limits. Water tube boilers, like those fitted to the LMS 5P in Britain, operated at 1,500 pounds per square inch and promised a 12% fuel saving over standard locomotives. The theory was sound, but the metallurgy lagged behind. After just 18,000 kilometers, a catastrophic boiler rupture ended the experiment. Safety investigators traced the failure to undetectable cracks in the alloy tubes, worsened by repeated cycles of heating and cooling. Maintenance crews lacked the tools and the training to spot these flaws before disaster struck. The lesson was as blunt as the failure. Pushing pressure beyond the material's endurance turned efficiency gains into safety hazards. For both the propeller railcar and the high-pressure steam engine, the hard stop was not a lack of imagination, but the refusal of physics and metallurgy to bend any further. Every experiment described here, from the Big Blow's turbine roar to the Q1 stripped-down Austerity, shares a lesson that goes beyond horsepower or headline speed. The true cost of a locomotive is not measured by its power rating or its initial promise, but by its entire life cycle. How it survives years of use, adapts to shifting fuel prices, absorbs maintenance, and fits within the physical and economic boundaries of a real rail network. Policy analysts and engineers studying these failures have distilled a simple checklist for any radical transportation project. Pilot before scaling, test under worst-case conditions, account for full life cycle costs, and ensure compatibility with existing infrastructure. This checklist is more than historical wisdom. Today, as companies race to deploy Hyperloop tubes, battery electric freight, and hydrogen-powered trains, the same risks reappear. Hyperloop test tracks reveal maintenance headaches and material fatigue that echo turbine blade erosion. Battery electric prototypes struggle with charging downtime and replacement costs, much as high-pressure steam engines struggled with boiler fatigue. Hydrogen propulsion, hailed as clean and abundant, faces the same infrastructure and safety challenges that once plagued bunker oil turbines. The pattern is clear. Technological ambition alone cannot outrun the realities of wear, cost, and complexity. Each failed locomotive leaves behind not just scrap metal, but a blueprint for how to test, question, and refine the next big idea before it rolls onto the main line. Every radical locomotive reveals the same hard truth. When ambition eclipses operational reality, even the most brilliant engineering meets the limits of physics and economics. Today's push for hydrogen and Hyperloop faces the same unforgiving calculus. Progress demands vision, but survival demands humility. The rails still remember both.